All right, let's talk about a science experiment so simple, it sounds like something you do in high school. You just shine a light on a piece of metal. But the result was so completely wrong, so baffling, it actually broke physics as we knew it. It took a young Albert Einstein to figure it out, and his solution, well, it completely changed how we see reality itself.
So what was the big deal? I mean, how could shining a light on metal cause a crisis in science? Why did this one observation, this photoelectric effect, have the greatest minds at the time totally stumped? Let's get into it, because this is a real mystery.
Okay, so to really get why this was such a headache, you have to understand what everyone thought they knew about light. And, at the time, their view made perfect sense. It was backed by tons of solid experiments.
Back then, everybody thought of light as a continuous wave. The best analogy is an ocean wave hitting a cliff. It's not one big punch, it's a constant, smooth delivery of energy that slowly wears the rock away. Physicists figured light worked the same way. Its energy should just sort of wash over the electrons in the metal, and eventually, once an electron soaked up enough energy, pop, it would get knocked free. Seems logical, right?
The experiment itself couldn't have been more straightforward. You had guys like Heinrich Hertz and Philip Lenard, and they'd put a metal plate in a vacuum tube, shine a light on it, and just wait. They wanted to see if electrons got kicked off the surface. Simple. What could possibly go wrong? Well, it turns out everything. This is where the story just goes completely off the rails. The results coming out of the lab didn't just disagree with the wave theory. No, they were a direct screaming contradiction to everything that was supposed to happen. And this slide just lays out the train wreck perfectly. First, the theory said a brighter light, more intensity, should hit the electrons harder, making them fly off faster. Makes sense. But that's not what they saw. A brighter light just knocked out more electrons, but their speed didn't change one bit. Weird. Second, the theory predicted that any color of light should work as long as you waited for the energy to build up. Wrong again. If the light was below a certain frequency, a certain color, nothing happened. Ever. It didn't matter how bright it was. And the final nail in the coffin? The time delay. Wave theory said a really dim light should take some time to charge up an electron. But in the experiments, the electrons flew off the metal instantly. So let's just boil it down. The physicists were staring at three clues that made absolutely no sense. One, there was this secret password, a threshold frequency, and if your light didn't have it, you weren't getting in. Two, the whole thing was instantaneous, zero time lag. And three, the energy of the electrons was tied to the light's color, not its brightness. The theory wasn't just a little off, it was completely, fundamentally broken. For years, this puzzle just sat there. All the clues were on the table, but nobody could connect the dots. And then, in 1905, a young patent clerk, Albert Einstein, comes along with an idea that sounded, frankly, a little crazy.
And this didn't just happen overnight. Hertz first noticed this weird effect way back in 1887. Leonard made his big discovery in 1902. But it was Einstein's paper in 1905 that finally cracked the code. And his idea was so out there, it took another 9 years before Robert Millikan's experiments proved he was absolutely right. So what did Einstein do? He basically threw out the entire rulebook. He said, okay, what if light isn't a continuous wave at all? What if it's actually a stream of tiny individual bullets of energy? He called them light quanta. Today, we call them photons. And here is the absolute genius of it. Each one of these little packets, each photon, carries a fixed amount of energy. And that energy isn't based on the light's brightness, but on its frequency, its color. So a photon of blue light simply has more energy than a photon of red light. Brightness? That's just how many photons are showing up every second. With this one idea, the whole puzzle just snaps together beautifully. See, it's not a wave washing over everything. It's a one-on-one collision. One photon hits one electron. It dumps all of its energy into that electron instantly. That's why there's no time delay. Now, if that photon has enough energy to overcome what's called the work function, basically the energy gluing the electron to the metal, the electron is knocked free. And any extra energy the photon had, that becomes the electron's speed. Boom. All three mysteries solved in one go. The best way to think about it is like a vending machine. Let's say it only takes $1 coins. You can stand there all day putting in pennies. That's like a bright light with a low frequency, but you're going to get nothing. It doesn't matter if you throw in 1,000 pennies. But the second you put in a single $1 coin, the right frequency, you get your snack. Instantly. More brightness is just more pennies. You need the right kind of coin. You need a higher frequency photon.
So Einstein solves this massive puzzle, gets a Nobel Prize for it, but the story doesn't end there. Not even close. This is where it goes from a physics puzzle to the technology that's literally in your pocket right now. Let's look at that legacy.
You have to understand, this wasn't just about fixing one little problem. The idea that energy isn't smooth and continuous, but comes in these little discrete packets, these quanta, that was the starting gun for the entire quantum revolution. This was the first real evidence that at the tiniest level, the universe is, well, it's chunky. It's not smooth.
And this isn't some abstract historical thing. The very device you might be watching this on, yep, the camera sensor in your phone or computer, that works because of the photoelectric effect. A photon hits a pixel and knocks an electron loose. It's how night vision goggles see in the dark. It even explains really weird stuff like how satellites get charged up by sunlight in space, or why moon dust actually levitates off the lunar surface.
But maybe the biggest, most mind-bending legacy of all is this. The old theory said light was a wave. Einstein's new theory said light was a particle. The shocking truth that we've had to accept is that it's both, at the same time. This idea, wave-particle duality, is a bedrock of modern physics, and it is just as weird as it sounds.
Which brings us to our final, deeply strange question. If light decides to act like a wave when you test it one way, and like a particle when you test it another way, what is it, really, when nobody is looking? That's a puzzle that goes way beyond a simple experiment, and it's one we are still grappling with today. Thanks for joining me.